Hey there, science fans. Imagine teaching a robot to play basketball. Cool, right? Our robot friend needs to learn how to shoot hoops perfectly. At first, its throws are all over the place. But with each miss, the robot learns and adjusts its aim. This learning process is powered by a brilliant technique called backpropagation. Backpropagation is like a coach inside the robot's brain. It helps the robot analyze its mistakes and improve its performance. Just like a basketball coach helps players by pointing out their errors and suggesting improvements, backpropagation guides the robot to become a true basketball star. This essay is your backstage pass to the exciting world of backpropagation. We'll explore how it empowers artificial intelligence to learn and evolve, just like our basketball playing robot. Get ready to unlock the secrets of AI learning. So, are you ready to unravel the magic behind backpropagation? Let's dive in. In the realm of AI, backpropagation is like a detective hot on the trail of errors. Its mission? To minimize those errors and make the AI as accurate as possible. Remember our robot friend? Every time it misses the basket, backpropagation steps in. It's like a coach reviewing game footage, analyzing every move the robot made. Was the angle off? Was the force too much? Backpropagation figures it all out. But how does it do this? By working backwards, of course. Backpropagation starts with the final error, the missed shot, and then traces its steps back through the AI's decision-making process. It identifies the culprits, the calculations that contributed to the error. This backward journey is the essence of backpropagation. Now that we know what backpropagation does, let's break it down further. Get ready to explore the fascinating steps involved in this error-busting process. Imagine a neural network as a complex network of roads. Data travels through these roads, making stops at different points called nodes. Each stop involves calculations that influence the final output, like our robot's shot. Step 1. The forward pass. The journey begins with the forward pass. Data enters the neural network and zips through the roads, making calculations at each node. Finally, it reaches the end, producing an output, in this case, the robot's shot. Step 2. Measuring the miss. Was it a hit or a miss? The output is compared to the target. The perfect swish into the basket. The difference between the two is the error. Step 3. Backpropagation begins. Now, the detective work starts. Backpropagation travels backwards through the network, revisiting each node. It figures out how much each calculation at each node contributed to the final error. Step 4. Adjusting the route. Remember, our goal is to reduce the error. Backpropagation tweaks the calculations at each node, like adjusting the route to avoid traffic jams. These adjustments are made to weights and biases, which are like the traffic signals of our neural network. The step-by-step process repeats until the error is minimized, and our robot is sinking baskets like a pro. But what's the secret sauce that guides these adjustments? Let's uncover the magic of cost functions. Section 4. Cost function. Measuring the miss. Remember the error we talked about? The difference between the robot's shot and the perfect swish? That's where the cost function comes in. It's like a measuring stick that quantifies the error. Think of it this way: the bigger the error, the higher the cost. Our goal is to find the sweet spot, the set of calculations that minimize this cost, leading to the most accurate output. There are different types of cost functions, each with its own way of measuring the error. It's like having different types of rulers, each best suited for a particular measurement. The choice of cost function depends on the specific problem we're trying to solve. Now, how do we find the minimum cost, the point where the error is the smallest? That's where the dynamic duo of chain rule and gradient descent come into play. Get ready for some teamwork. Section 5. Chain rule and gradient descent. Teamwork makes the dream work. Remember the network of roads in our neural network? The chain rule helps us understand how a change in one part of the network affects the final output. It's like figuring out how a traffic jam on one road impacts the overall traffic flow. Once we understand the impact of each calculation, we need a way to minimize the cost, remember? That's where gradient descent swoops in. Imagine yourself standing on a hillside and wanting to reach the bottom. Gradient descent is like taking small steps downhill in the direction of the steepest slope. In the context of backpropagation, gradient descent uses the information from the chain rule to figure out how to adjust the weights and biases at each node to minimize the cost function. It's like taking those small steps downhill until we reach the lowest point where the error is minimized. This powerful combination of chain, rule, and gradient descent is the engine that drives backpropagation, making those crucial adjustments to weights and biases.